In this video, we are going to solve the two-sum problem from LeetCode. In this problem, we have a list of numbers, and we need to find two different numbers that add up to a given target. For example, in this list, we need to find two numbers that add up to 9. If we add the numbers at positions 0 and 1, we get 9. So we return a list with those indices, 0 and 1. In another example, we have to find two numbers that add up to 6. In this case, the numbers are at positions 1 and 2, so we return a list with those indices. To solve this problem, we'll go over 3 different algorithms, each one more efficient than the last. The first one is a brute force algorithm where, using a double loop, we'll check all possible pairs of numbers. Let's see it with an example. We are going to loop through this list using a variable I, which starts at index 0. For each I, we check the remaining numbers to its right using another variable j, which starts at I plus 1. For each pair, we add their values and check if they match the target. If not, we move j one step forward and we repeat until we reach the end of the list. If we reach the end of the list without finding a match, we move I one step forward and we restart the process. This time, I is 1 and j starts at 2. We continue checking sums until we find that 9 plus 5 equals 14, which is our target. That means that our solution is a list with the indices 1 and 4. Let's see it in code. We create a loop for I from 0 up to the length of the list, and inside it we create a nested loop, where j starts at position I plus 1 until the end of the loop. For each combination of indices, we check the numbers at those positions in the list to see if they add up to the target. If they do, we return a list with their indices. This algorithm has a time complexity of n squared. Since we don't need any extra storage, the space complexity is O of 1. Even though this approach works, it's not very efficient, so let's move on to a better one. Algorithm number 2, sorting plus 2 pointers. Let's use the same list and target, but this time we begin by adding the indices to each element of the list to keep track of their original position, and then we sort those elements by value ascending, from smallest to greatest. Then we introduce 2 pointers, I at position 0 and j at the last position of this sorted list, and we sum the values that they point to. For example, with a target of 14, the sum starts at 11. Since 11 is too low, we move I one step to the right, but since the next element is also at 2, the sum is still 11, so we have to move I to the right once again. Now the sum is 12, which is still too low, so we move I one more time to the right, and we finally get 14, which is our target. Therefore, the solution is the indices in the original list, not the sorted list, associated with those numbers, which are 1 and 4. But let's see it in code. First, we create a list of tuples, storing each element in the original list along with its index. Then, we sort this list, and we initialize I at the first index and j at the last. While I is less than j, then we check the sum of the elements at those indices. If they sum to the target, then we return a list with those indices. If the sum is too low, we move I to the right. And if the sum is too high, we move j to the left. And if there's a valid combination in this list that matches the target, this algorithm is guaranteed to find it. Okay, and the complexity of this algorithm has gone from n squared in the previous one to n times the logarithm of n, because although we can find the winning combination in a single pass on the list, we first have to sort this list, which is done in n log n time. The space complexity is O of n because we have to create a new list to store the elements of the original one along with their indices. This method is much better than the previous one, but I think we can do better. So let's go to our third algorithm, using a hash map. Using this approach, we'll be able to solve this problem in linear time. We have our list and our target, and now we are going to create a dictionary that is a hash map, to store values with their indices. We go through the list only once, and for each number, we calculate the number that is missing to get to the target. For example, in our case, we start with 3. The number needed to reach 14 is 11, but the dictionary is empty, so the necessary number is obviously not there. That means we insert 3 as a key in our dictionary with its index as its value, and we keep iterating. We move to 9, and the number needed to reach the target is 5, which is not in the dictionary, so we add 9 as a key and 1 as a value. We continue to 2, which needs a 12. Since 12 is not in the dictionary, we add 2 with its position, which is also 2. We move on to the next element, which is 2 again. So to get to 14, we need a 12. Since 12 is not in the dictionary, we insert again 2 as a key and we update its value to 3. Then we get to 5, and 5 needs a 9, which, as you can see, is indeed in our dictionary. And that means we have found our solution, which are the indices 1 and 4. Let's see it in code. We create an empty dictionary and we iterate through the list. For each number, we check if the required value is in the list, and if it is, we return those indices. Otherwise, we store the number in the dictionary and we move on. This approach runs in O of n, both in time and space. And that's it. You've seen 3 ways to solve the two-sum problem. If you found this helpful, subscribe and hit the bell so you don't miss more videos like this. See you in the next one, and happy coding!